Hello Internet and fellow network engineers. My name is Maxim. I share network design ideas, tips and tricks with you on my channel. This video is the third and final dedicated to Source Network Address Translation or NAT. Are you aware that your Source NAT session count can be actually several times more than available ports in your pool? Do you know that it is totally okay to use the same exact public IP address and in the source and destination NAT at the same time? Are you curious how to downsize your source NAT pool to save on OPEX, but not sacrifice functionality or scaling? You came to the right place. The third video is focusing large-scale source NAT solutions, which can be found in large campus networks, data centers, or internet service providers. Hardware in my demo and designs is represented by Juniper SRX series firewall, which is available in a wide range of models, from the smallest fanless desk solutions like that, up to the chassis-based models with performance measured in terabits per second. Large-scale NAT solutions can be implemented using Juniper SRX data center series models, starting from fixed form factor, SRX 2300, 4600, 4700, and chassis-based SRX 5000 series. For this type of solution, redundancy is a must. Very tight requirements to any possible downtime and high performance demands. Dual ISPs with high-speed interface peering options like 10 gig, 40 gig, 100 gig, and even 400 gigabits per second sometimes in DC CGNet scenarios. I will start with briefly discussing technology basics, then go over 3 design solutions, and finally I will show you a lab demo with hands-on and configuration samples. Let's start with some basics. The whole range of IP addresses can be separated into public address space and private address space. Public address space is the routable in the internet address space, which is being registered and owned by different companies and internet service providers, while private address space is a dedicated address space which is allowed to use for everybody in order to conserve the public address space. But there is a catch, so private address space is not publicly internet routable, and if hosts with the private addresses needs to communicate to the internet, this needs to be translated. This is called the Source NAT or network address translation. So this is the whole topic of conversation in this video. And also public address space can be separated into portable and non-portable. Again, as I mentioned, public is very similar to like car license plates, which are dedicated and reserved and registered to certain companies. Portable address space, this is when company is using the address space which it owns, which belongs to her. And non-portable is something different, is like renting, for example, a public address space from an ISP, like a subnet from the internet service provider. In this case, you have certain restrictions how you can use this address space. This is just a general topology diagram for like internet, which consists of different networks, private and public, but the internet itself talks only on the public addresses. It means the green networks can communicate via green links because they are publicly routable. All the brown bubbles needs to be translated by some device, which is usually a firewall, and this process, when private address is being translated to public address, is called the network address translation. Port overloading factor. This is a setting which can be applied for the interface NAT or for a certain pool, and it affects how pool is utilized and how scalable the pool is. Let's say we will set at the example of just one IP address. If you don't use port overloading factor, which equals it set to 1 by default, you have a general pool containing all the available ports for your translations. And when the session is being ready to being established, it just takes one address from the pool and being translated. And the example, if the port overloading factor is set to 4, this is when there are basically 4 copies or 4 subpools are created containing all the available ports for that one IP address in this example. And then there is also additional step in the process by doing the certain hash operation on the destination address and selecting which pool this specific session will be using a port from. And basically, it gives us the possibility to increase the potential pool size by not increasing the IP addresses in the pool itself. And as a result, at the same time, there can be multiple sessions using the same port for translation. And every single session will always, based on the hash algorithm, will always hit just one of these pools, not multiple. And you can also influence the number of these pools, which can be set by this factor. It can be from 2 to 32. Let's look into the pool depletion scenario, because there is important and there is a difference here between the two approaches. The first approach is very simple. If all the pool ports are shared, it means as soon as they are depleted, the session is dropped and no more sessions can be established. But in case of the overloading factor use case, remember the hash algorithm. So different sessions are being hashed to a different subpool. And if you have high utilization on one of the pools, let's say one pool is depleted, all the sessions which are based on the hash algorithm are hitting this pool will be dropped. The sessions will not be using ports from other subpools, even if there are available ports still there. So this is something to remember. So how can we scale it? We can. So basically what can be done, if you increase the pool size to 2 addresses from 1, you increase the available port density, right? 2 times, up to 124,000. And it basically will be in every subpool. Increase will be in every subpool, so which is great. But there is a catch. The maximum interfaces in the pool with a non-default overloading factor depends on the Juniper SRX model. And on the branch series or the virtual product, it is limited to 1. In the data center product, it starts increasing. Like in 1500, you can create a pool of 2 addresses and apply non-standard factor to it. Or big boxes like ISP and data center scaling, they can do up to 128 addresses. And there are actually fun facts. A pool of 128 addresses can give you potentially just shy of 8 million sessions for NAT translation. But if you have, let's say, SRX 4600 with the same pool of 128 addresses, but with the port overload factor enabled to 32, the maximum value, you have a theoretical pool size of over 255 million sessions. This is something very important for the ISP scenarios like carrier-grade NAT or CGNAT. On this slide, we can see a lab topology, which is being used in this series of videos. This specific video is targeting the large-scale headquarters or data center type of scenario, which is in the top portion of the diagram. The devices being used are Juniper Virtual SRX and Virtual MX with the versions mentioned here. Also, the routers in the middle are simulating internet service providers, and there is the target test server, which is emulating the server in the internet where we'll be sending test traffic to. Next, we'll continue with the large-scale use case, scenario 1. In this case, the redundancy comes to a first place. We have 2 ISPs peering with us with a /30 P2P subnets. Routing is still static. In this case, we have 2 non-portable pools be rented from each ISP, from ISP1 and ISP2. The difference in this case, as I mentioned, non-portable belongs to ISP. So we cannot, let's say, pool rented from ISP1 can never be advertised to ISP2 and vice versa. So in this case, for simplicity, the forwarding schema for the ISP is done in the active backup scenario, when all the traffic is going to one ISP under healthy circumstances and fails over to the secondary ISP only if the primary ISP goes down. This is important to mention that you can also notice that the pool size stays at 250,000 sessions with the port overloading factor set to 1. The reason behind it is that it lays in our active backup forwarding schema, so we can use one NAT pool at a time. So let's say if ISP1 is the primary way out, we use ISP1 pool, but we don't use ISP2. And we start using ISP2 pool only when ISP1 goes down. So let's go and have a look at the lab demo. Let's start with the configuration review. Again, we'll just look through the whole configuration and then we'll look through the details. So as I mentioned before, we have two pools. One is non-portable, provided by ISP1, containing 4 addresses, and one is non-portable, provided by ISP2, also 4 addresses. In this case, again, because we have 2 separate pools, we have 2 separate rule sets. And the difference between these 2 rule sets is the to zone, right? So if the traffic is coming from the trust zone and going to ISP1 zone, we are using Source NAT pool, ISP1 pool. If it is coming from trust to ISP2, we are using ISP2 pool, right? So basically, if you look at the SRX internal processing steps, a route lookup will always be happening before Source NAT. And it gives the idea that when the pipeline will reach Source NAT, it will already know the source and destination zone. It means that the route lookup will decide what interface will be outgoing, and that interface, what zone that interface belongs to, is basically plays a role here. So by using the certain routing decision, we affect what pool we use for the translation. Again, we have two separate security zones, just because we have to place our 2 provider-facing interfaces into 2 separate security zones, which are ISP1 and ISP2. Another moment is our routing. As I mentioned, it is active standby, static routing. So it basically points to one of the providers, right, which is ISP1, and we use it as primary. It is using route preference 5 by default. And we also create a floating point static route to our secondary ISP with a higher preference, which is worse. So let's have a look at our route. This is how it looks like in the routing table. As I mentioned, we have a preference 5 pointing to the ISP1, and then we have a less preferred route pointing to the ISP2. So the next step is we'll verify our show security NAT source summary. So let's have a look. It will basically, again, notify us that we have 2 pools, right? And also 2 rule sets, right? One is from zone trust to zone ISP1, another is to ISP2. And if you look again at our routing, so let's say currently the test traffic, which will start in a moment, let's basically do it. So this one will start ICMP ping. This one will start TCP ping. Okay, so it's going. And in our case, basically the idea is simple. It is checking routing table. It is seeing that interface as an outgoing. It is checking, okay, what security zone does this interface belongs to? This interface belongs to ISP1 zone, right? And it means, okay, what NAT I need to use? I need to use NAT which is outgoing to that security zone. So this is basically the sequence of steps, and then it is using this pool. So we have test traffic successfully going. So our next step will be show security NAT source rule all. Yeah, so in this case, output is a little bigger because we have 2 rules, right? And then we can see translation hits. This pool is being used, right? Number of sessions 5. But while this pool is completely idle, right? Remember that, again, it's active standby schema. We are not using this pool actively until there is a problem with the main pool. Then we are doing show security flow session. Yeah, so we are seeing some sessions coming from the host 1. Okay, yeah. So we just need to catch a certain moment. So we see a TCP session. Again, it's being translated from private to public, right? 103 belongs to ISP1. So we can see we are using actively pool 103, which is ISP1, right? All the sessions are being going through and being translated properly. Well, let's do next command. Show security net source net source resource net resource usage source pool, and then we again we have 2 pools. First, we'll check for our ISP1 pool, and we can see again it is equally being used. There is no port overload factor set, right? It's just 4 individual addresses, and they being equally used at the moment. And then we can verify our ISP2 pool, which is not used at all, right? So again, because it's standby. So the next step I have here prepared, so I can do ping from another virtual SRX, which is acting as a host. But in this case, what I can do rapid ping. So in this case, we have more traffic, and we can verify how our utilization looks on the ISP1 pool. So you can see it's almost equal in terms of utilization. So these are individual sessions are being translated, because every single ping, request and response, this is actually a dedicated session. But if we do ISP2, it's still idle, right? Because we don't use it. So it's just confirming it. So next step, what we are going to do, we are going to check our flow table, security flow session table. And what we are going to do, we are going to shut down our primary ISP interface. And it is GE001. We can also see it right here. So this is where we expect the return traffic to come from, right? So we are doing set interfaces GE001 disable. We are doing commit, and we are verifying our test traffic. Our test traffic is still going, but remember, these are individual sessions being established like every second or so. And we do show security flow session, and we can see that now all the traffic is being translated to our ISP2 pool, right? And vice versa, if we do now pool resource usage, we can see that our ISP1 pool is not used, and our ISP2 pool is being used, right? So, and if we check our routing table, we can see that the primary route is gone because the interface is in down state. So now what we are going to do, we start our rapid ping as well. And then we are going here and we are going to do rollback 1. So we are bringing our primary interface back up. And as soon as we do it, our route immediately appears, right? And we can see that our primary pool, ISP1 pool, immediately starts working. And our pool 2 immediately stops, right? So it basically means that if we have a certain failure scenario, failover scenario between ISPs, unfortunately all sessions will be gone because these are 2 separate pools, right? We cannot forward ISP1's non-portable addresses to ISP2 and vice versa. So this is something to know in terms of redundancy. Yep, so this concludes this lab demo. Let's return back to presentation. Next, large-scale use case scenario 2. In this scenario, we consider our company having its own autonomous system number and also its own portable address space, including our portable /29 public subnet, which is dedicated for our Source NAT use case. The difference in this case is that now we have 2 ISPs as well, but we are peering with the eBGP protocol, and we have BFD for fast issue detection. We are advertising our portable pool to both ISPs. This is an advantage of having portable. And as a result, we have a portable pool of 8 addresses. All 8 addresses will be used all the time. We don't waste addresses like in the previous scenario. And we can estimate our available pool size for about 500,000. And port overloading factor is set to 1, the default. Let's go and check in the lab. We'll start with the configuration review. So this use case will be significantly different from the previous one. So let's look into this. So we create a portable pool, so a single pool containing of 8 addresses. Remember, this is a portable pool, so basically belonging to this organization. In this case, it basically simplifies everything. So let's look from the bottom. So we have, not from the bottom, from the middle. So we have, again, 2 ISP-facing interfaces configured with P2P, right? But now the difference is that we don't need to have 2 different security zones. We would like to simplify it and make it a single security zone. You can notice that we have security zone untrust containing both interfaces, going to ISP1 and going to ISP2. We enable certain host and bound traffic to make sure that BGP and BFD will run properly. And also now, because we have just 2 security zones, it's just simply one single rule set with a single action mentioning portable pool as a source NAT pool. Another important piece is that in our scenario, we would like to have active-active forwarding. So to achieve active-active forwarding, there are actually 2 steps. When in the BGP group configuration, we need to mention multipath, multiple AS, which will allow routes to be equally used for BGP routes coming from different AS numbers. And the next step, this enables ECMP behavior in the control plane. We also need to enable it in the forwarding plane, which we use the policy for. Yeah, this is you enable then load balance per packet or per flow in the modern code, and then you apply this policy on the routing options forwarding table. So this enables the forwarding plane, data plane, ECMP behavior. So this is set and done. We also configure our own autonomous system, and we create some kind of like our aggregate routes, our summary routes for our portable, like big, large portable block. It has to be at least /24 to be routable in the internet. And then we use a dedicated policy to advertise this summary route inside the BGP to our ISP1 and ISP2. And then basically we apply it as an expert policy. It is very important to apply the deny policy in this case, because we don't want to make our network a transit point for traffic coming from ISP1 to ISP2 and vice versa. We just advertise our summary block, portable block, and then we drop everything else. So this is it. We can also make the forwarding decisions more efficient by using layer 3 and the layer 4 information in the hashing process. So that's basically it. So next step will be show security NAT source summary. So it will show us that we have a single pool containing 8 addresses. So next step will be we'll start our test traffic, which is ICMP ping in both scenarios. So we'll change it and send ICMP traffic from both hosts. It is going successfully, and then we'll do show. There are a few more steps which we need to do. So let's do show BGP summary. So there are 2 sessions established with the providers, right? So then important piece is show routes for 5555, right? So in our case, we have 2 next hops, basically our ISP1 and ISP2 in the ECMP scenario. Then we need to verify that we have actually ECMP in the data plane by doing show route forwarding table destination. Yep, and we can see there are 2 next hops. So we are doing actively ECMP to both providers. And also one more step, show BFD session. So we are running sub-second detection BFD sessions to both providers to fast detect issues if something will be going on with the last mile. So next step is show security flow session, right? Our test traffic is going. Yep. So let's have a look. We have again same. That is our idea. So the private address host 1 is being translated to the public, and then private address 2 is being translated to the public. But this is not the most interesting part. This is the most interesting part. So this is actually outgoing interface where we forward traffic out and where we like potentially expect it coming in. And you can see that for that specific host, it's being sent out of G001, ISP1, and for 2, it is sending it to G000, which is ISP2. So we are indeed doing ECMP forwarding. So next step is show security NAT source rule all. So we are checking our rule, and basically just statistics and number of active sessions at the moment. So as before, show security NAT resource usage source pool, and then we use our portable pool. In this case, we can see our 8 IP addresses. We can see the usage, right, and available, and we don't use port overload factor in this scenario. Next step, we'll run a rapid ping, right, and we'll basically go back and we'll check the resource utilization again, and we can see again it all perfectly equally distribute the load between IP addresses in the pool. Show security flow session. Okay. Yep. Okay, we are using different IP addresses from the pool. Yeah, and basically for the ICMP, it is looking just at the IP address source destination pair. So that's why all the traffic coming from the host 3, which is the SRX rapid ping, it is all going out of single interface. So because it's not like a UDP or TCP. To more efficiently use ECMP behavior for that kind of traffic. So it is using just protocol and source destination IPs. So next I'm going to do something interesting. So I'm going to establish from the host, I'm going to establish an SSH session to the internet host. So this host has a private address, and it is now this TCP SSH session is going through their firewall and is being source translated. So I'm going to, again, session is established. So now I'm going to run like a general command by doing refresh 1. Refresh 1. So it will basically generate output and generate some traffic for us. But now we are going back and we are doing show security flow session on our firewall. We find this session, there it is, SSH, right? So we see some bytes going in and out, but the most important piece for us is what is our interface, which is again outgoing, right? So it's basically ISP1, so where it is currently forwarding this session. It is translating it, right? And then we copy the session identifier, and then we do show security flow session identifier, and then we paste the session identifier. So we'll be closely monitoring this session, which is currently around a minute. And again, this is the interface, right? Show interfaces descriptions. So this is how it is currently going out to ISP1. So what we are going to do, we are going to test the advantage of using the portable solution with a single security zone. So we are going to shut down our primary ISP. Thanks to the BFD, we have sub-second detection, and we'll be able to quickly switch and make sure that the traffic is going back properly. So we can see that traffic is already, basically session is keep refreshing, right? We also have our ICMP traffic going. So there was just one packet lost. Yeah, and for this client, no packets were lost. So we are going to do show routes for that 9991 host. And currently it is pointing to the ISP2. And what we are going to do, we are going to do show security flow session and find our TCP session, SSH session. There it is. And now you can see interface changed to ISP2, right? And if I go and check our previous commands with our previous session identifier, it is right here, right? It's now just about 3 minutes. But it is here, just interface changed, right? Because it is ECMP, same security zone. For the firewall, the security zone important, not the interface. And the session is, again, perfectly responsive, right? So what we are going to do now, we are going to roll back our change. Right? So we are going to bring back show BGP summary. So you can see currently it is idle. So I'm going to commit. And then I'm doing show BGP summary. So in a moment, yep, session is established. So and then I'm doing show route 9991. So we can see that again we are back to our ECMP behavior. And then I'm doing the same check for the session, right? Session is still there, right? It's just about like almost 6 minutes, right? And then we can notice over here that interface stayed to be ISP2, right? So there is no reason to change it back. So we're just using that interface, right? Regardless of the one is coming up because it's ECMP behavior. Yep, and we come back and we verify our session. It's still refreshing and it's perfectly fine, right? So it means in this scenario, you have a link redundancy, you have ISP redundancy without losing a session and any impact to the traffic. If you have certain proper BFD timers set. This concludes this lab demonstration. We'll also touch briefly scenario number 3, which is identical to the previous one, but let's just imagine that we would like to save some address space for other purposes. And in this case, we can shrink our pool from /29 to /30 down to 4 addresses, while also enabling port overloading factor. In this example to 4, which brings our total pool size up to 1 million sessions, excluding twin port count. For this scenario, I won't show you the demo in the lab, because in my lab I use SRX for the demo, so it doesn't support more than one interface in the port overloading factor pool. This is an example outputs from SRX 4600. On the left side, we can see configuration. So I just set 4 IP addresses, overloading factor 4, and also use a pool utilization alarm feature, which I highly recommend especially for the very important network segments. So if the utilization goes above raise threshold, it sends SNMP trap. And this is the resource usage command on the right side, which basically shows our pool statistics, the total ports, including twin port. And then for every single IP address, we see 4 subpools based on our factor settings. Here we are. Thank you for watching, and I hope you learned something new or useful today. See you in the next video.